guy, for example, fn of x minus, say for example, t, it's a continuous function. Would you agree that it's a continuous function? So it's like t is mapped onto fn of x in t. So the t is from where? Okay.
Enter omega.
T is an omega, and fn of x minus t is basically a continuous function. Why it's a continuous function?
Fn of x is continuous.
No, it's bounded.
Bounded is continuous.
Bounded.
T is continuous. T continuous.
Yes, I mean, exactly. This is like a fixed number. This is like a fixed number. So this is like something 2 minus t. Something like 2 minus t. So 2 is like a fixed number. That's a continuous function basically. So the real variable here is here ti. Okay. So it's a continuous function. So if it's a continuous function, so in other words, if I fix this guy and I keep on varying it, okay, then say that since I'll mention it again, that function that I wrote is a continuous map. So what I can do, I can take this limit inside basically. So if I'll take this limit inside, okay, so this is the limit of x minus, this is going to be what in particular f(x), because this is what the definition is. As m goes to infinity, okay, I'm putting limit here because m can be anything else, anything as well. Nothing. So in other words, what we are saying is take the both limits. Limit m goes to infinity and limit m goes to infinity. Okay. M goes to infinity and limit m goes to infinity. I can kind of put it inside because of the continuity of the function that I mentioned. This expression, essentially. And as I said, why this is true? Because this map t from omega into fn of x, into k, okay, is a continuous map. It's continuous. If it is continuous, I can put this limit inside. And what? I know that I can estimate this limit by, can I say that I can estimate this limit? So it's like, so if fn of x and fn of x is less than epsilon for all n bigger than or equal to n, so I can say that this is going to be also less than or equal to our this arbitrary epsilon. Okay. The next thing is what? Next thing is to turn this expression, okay, into what? Into the infinity norm expression, so that I can estimate this by epsilon. The question is, how can I turn this into the infinity norm expression? By just taking the suprema map. Okay. So that if this can be estimated for any n after capital N and any fixed x, okay, then I can say that the supremum of, so it's like if this is an upper bound for all such expressions, so it's going to be also upper bound for the supremum. So if you take supremums in the last expression, what are you going to get? You're going to get Fn minus f in infinity norm can be estimated by epsilon whenever n goes beyond 10. the limit. Okay. You can ask, where does this limit goes? Well, this limit is here. This is another way of writing this limit, essentially. Okay. So what does this shows? Taking, should be more explicit that I am taking the supremum over x. Very much explicit. What does this shows? This shows that this sequence fn converges to fn. Okay. So the convergence is kind of done. The only thing which kind of remains is to still we haven't shown that whether f is part of p of omega or not. So how can I show it?
Bounded to
This is what that we have to make sense of. What do you think that? The trick would be something similar that you did in case of F2. So f can be written as f minus fn plus fn capital N for. Okay. Even if you don't have, still this is true. And then just take the infinity norm. And I know that I can estimate this by f minus fn in infinity norm plus fn infinity norm. Okay. Now this guy is smaller than or equal to epsilon. Okay. And this guy, why this guy is finite?
Already b omega. There is already
Because we have assumed that this sequence is in b of omega. So if it's in b of omega, like this guy must be finite. Well, for this, I've shown that this is an estimate. So this guy is affinite. So if it is infinite, it's belongs to capital B of omega. And this shows that B of omega with the infinity norm is complete. In the sequence of all bounded functions over a non-empty set is a Banach. And obviously, in particular, it also follows by taking omega to be say set of natural numbers that L infinity is a Banach set of all bounded sequences in K is the Banach space. Do continuous function has any relationship with bounded functions? What is that relationship?
Every continuous is bounded.
In other words, if I take space of continuous function over certain interval, it would be subspace of this B of omega. Okay. So the last example for today is that example of Banach space in that CAB. We saw that CAB is not in Hilbert space. Okay, with respect to norm. But we're going to show that it's a Banach space with respect to the infinity norm. Banach space with respect to infinity norm. So that's a very important question actually. So, to ask that, if I say that some space is complete, we must ask that with respect to what topology. Okay, it's not that, just that, okay, it's complete in general. It must convergence, is topology dependent, and depends on that what norm you have there, what metric you have there. Okay. The strategy to prove thing is going to be this. I'm not going to take an arbitrary sequence in it and Cauchy sequence in it and show that it converges. Okay. But I'm going to take another path, and that path is that kind of we know that CAB, okay, is what? Is a subspace of calligraphic B AB. It's like subspace of all bounded functions of lambda A. So what I'm going to show, and I know that like this guy is a Banach space with respect to infinity law. I'm going to show that like CAB is also complete with respect to this infinity law. Okay. And for this it is sufficient to show that every element.
Not CAB,
No. Just showing subspace is not sufficient. So I need to show that this is a closed subspace. We know that every closed subspace of a complete space is complete. Okay. So essentially, what should I show in order to show that this space CAB is complete, closed? What I need to do, I need to take a sequence from CAB, okay, and I need to show that it converges within this space. This is what essentially we have. So let Fn. N is here. The convergent sequence. The convergent to some Fn to some affect. Uniformly. What do you mean by uniformly? I mean that is in infinity now. Like if you have a convergence in infinity now, we call it a uniform convergence. And I'm not assuming for f that where does it belong. So obviously there is going to be somewhere in your I show that this is also an element in CAB. So this is a continuous map on the interval CAB. So that the claim is that F indeed belongs to CAB. To be more specific for each x in the interval a to b, f of x is continuous. F is continuous at x. Continuity of f can follow from this uniform convergence. And in order to show continuity, what we need to show?
Convergence equals
just like our definition of continuity. We are following that continuous maps are those maps which map convergent sequences onto the convergent sequences. So what I need to show, I need to take a sequence in the interval AB, which is convergent to some point in x and AB. I need to show that
F of
if
x.
f is going to map that convergent sequence onto a convergent sequence in K. Okay? So let xm be a sequence in A to B. Okay? Sequence in A to B. And such that this xm converges to some x. This x actually, let me have fix as f goes to infinity. And we want to show that if you map this sequence under f, you still have this convergence. Okay. So what I need to show that if I map this xm under f and x this under f, this goes to 0 and then goes to infinity. Okay? Give me an estimate on this and keeping you all this information with yourself. And my claim is that I can estimate this by what? I can estimate this by 2 times of, so if I take a supremum over here and here, then I can estimate this by 2 times of f minus fn in infinity long, okay, plus fn of x minus fn of xm, okay, alright, and what, are we done? You think that y is sufficient to include what we want? So you see that you have this uniform convergence. This guy goes to 0 as m goes to infinity. Why this guy will go to 0? Why? Because fn is a sequence in CAD. So if it's a sequence of continuous functions, so I know that continuous function map convergent sequence onto the convergent sequence. So if xm converges to x, then fn of xm will converge to fn of xm. So in other words, this guy goes to 0, okay, as an m. This is what we wanted to show. Okay. Okay. First thing that we shown, that's how if I collect this information, what does it show? Oh,
Because xm goes to x, f of xm is equal to
goes to
f
f of x as an f.
that is continuous. And then it comes to CAV and then you done.
Okay. So roughly, so this argumentation is called what you call 3 epsilon argument. You can read it more precisely from here, but essentially crux is there. That F is a kind of a map which kind of is kind of point-wise throwing convergent sequences on sequence, which is a key property. As you know. ठीक है? You can see a more precise version here. Just read it for yourself. Essentially, crux is this. Essentially, so we are almost done with this chapter. Okay. So the last thing, a very specific thing that I would like to write, imagine that this CP of omega, okay, is the space of all maps which are bounded over omega, and such that F is continuous as well. So the set of all bounded continuous map. What would be the key difference between this and the CAB? There you have only continuous functions, right? Here you're talking about all bounded continuous function over an arbitrary omega. Over an arbitrary omega space. Okay. F is continuous. It's like space of all bounded continuous function, you denote it by the CP of omega. We can show that this guy is a closed subspace. Argument is going to be essentially analog. That is closed subspace of calligraphic V of omega. Infinity norm, and hence must be complete. Okay. So I'm saying that the space of all continuous and bounded function over the omega, arbitrary omega, is a closed subspace of this guy. This boundary space. So what is it going to show? That the CP of omega, space of the bounded continuous function, is the Banach space. You must also focus on reading books because there are lots of interesting comments that you will find actually. I can't go through each and everything from the book. Obviously, I will try to hit the high points. Okay. Try to read almost everything in the chapter, especially this chapter. This is very important. The last thing I want to add, basically is what we call the series in Banach space. Okay. Series in Banach space. I would like to kind of roughly define that. What would be a meaning of a series in convergent in Banach space? and then finally I'll give a result, which is kind of also a characterization of Banach spaces as well. That okay, you always don't need to take this population stuff up. You have another characterization in the terms of series is that if you have that, you respect the Banach space as well. Okay. Here's the question. Imagine is a normed space, okay, and I have a sequence E. And find be a sequence in E. The question is, if I kind of give you a right to define, I'll give a meaning